What is going on, everybody, and welcome to the future. Welcome to part 3 of the quantum computer programming tutorials. In this tutorial, we're going to be getting into our very first algorithm, which is the Deutsch Jozsa algorithm. Now, this algorithm is relatively pointless in what its actual outcome is, but instead what it's good for is two things, really. One is it really is an algorithm that is provably faster than a quantum computer in terms of how many, like, say, cycles through the circuit are required to get the answer. But also the reason it's more so, it's not just the speed, it's why is it faster. So this is the first time you should get a real idea and feeling for how is this working, and why is this working, because the reason why it works is the circuit is able to consider all of the possible inputs that could have come into the circuit, and it can immediately respond with the output. So, and the output is not output based on input, it's output based on the nature of the circuit. And so that's what's cool about this algorithm. It's not the actual result of the algorithm, and I think that point gets lost on a lot of people. At least when I'm looking around at explanations and stuff of the Deutsch Jozsa algorithm, as well as some of the others like the Bernstein-Vazirani and even Shor's algorithm. Although I think most people understand, oh, it breaks encryption, cool, okay, but the Deutsch Jozsa algorithm is the inspiration behind Bernstein-Vazirani, Shor's algorithm, and I'm sure many others, because it shows, and this was kind of the first one that shows, oh, you can do this stuff. Like these are things that you just can't do with a regular classical circuit. So let me just formulate really quickly. I don't want to spend too much time explaining the problem, but it would probably be useful to explain the problem. So with the Deutsch Jozsa algorithm, you've got a function, right? So the function is your black box, and let's say you're going to pass a 2-bit string to this box. And the question that we want to answer is this black box going to output a constant output, or will the output be a balanced output? So will this box always output all zeros or all ones? Or will it output zeros and ones in a balanced manner, so an even number of zeros and ones? So with a classical circuit, the only way that you could find this out is at minimum you would need 2 outputs from the machine. So if we got a 2-bit string, it's going to take at least 2 queries, because on the second query you could find that, oh, let's say on the first query the result is a 0, 0. The second query you got a 0, 1, right? And when I say query, I mean like pass through the circuit. So to find out if a circuit is balanced or constant on a 2-bit string, it's going to take at least 2 passes. As we increase the number of bits in the string that we want to pass through this function, it's going to take longer and longer and longer for a classical circuit to be able to make this determination. A quantum circuit, on the other hand, can make this determination regardless of how long that bit string is in one pass. And this is what shows the power of quantum circuits. And again, the problem itself is not useful. It's just, this is the most basic representation that we can come up with that shows the attribute that quantum circuits have that classic circuits do not have. So don't get hung up on the problem. Get hung up on why this solves this problem. So with that out of the way, let's go ahead and get into it. So to begin, this all rests on a term that I'm going to coin as Hadamard sandwiches. So again, like I said in part 1, I'm not a quantum physics expert, okay? I'm not even a physics expert. I'm really not an expert of anything. So remember, you're just watching a dude on YouTube. So I'm going to use words here that I feel describe what's going on, but they're probably the wrong word. So yeah, just bear with me there. If you're like an actual, PhD person, feel free to correct me and tell me that the word is correct. And if I've somehow stolen Hadamard sandwiches, I apologize. I'm pretty confident I've never seen that anywhere, but that's what it looks like. It's just Hadamards on all the sides. So you're just squishing something between Hadamards. It's It's a Hadamard sandwich. So anyway, if there's an official term for it, let me know. So to begin, well, we're probably going to need some of our initial imports, huh? I don't really want to type this out. Everyone should have these, so I'm not going to do that again. It's a waste of time. So we will have Qiskit. We'll have our, I did check this, by the way. I'm sure by the time this video is coming out after part 2, and I'm sure people will correct me, but I don't know which one is the new one, but this happens all the time in libraries. I'm going to go with the shorter one. But you can import both of these from the shorter one, so cool. So, yeah, all this stuff is stuff you've seen. So the first thing I want to do is show you this Hadamard sandwich on what I'm also going to call uncertain qubits. And when I say an uncertain qubit, this is a qubit that will collapse, not always to the same answer. So to begin, let's say we've got a circuit, and that's going to be a quantum circuit, and we'll make it a 2 and 2, so 2 qubits, 2 classical bits. And then we'll say rotation on the y, and we'll go with math.pi divided by 4 on qubit 0. And then we're just going to do the same thing to qubit at index 1, so that's our 2 qubits are done. And then what we're going to say is I'm going to call this orig state vec, and that's going to be equal to q.execute, and we're going to execute the circuit on the back end of this state vec simulator. So just remember, if you want to get the state vectors, you have to do it before you actually take the measurement. Otherwise, the circuit will have collapsed, and the state vector won't work. I mean, it'll work. It just won't give you what you hoped. So state vec sim, and then we're going to say .result.get state vector. So now we have the actual state vec, and then we will c.measure, and then we're just going to measure both qubits to both classical bits, and then we'll do a c.draw. Oh, q.quantum circuit. I see. Q.quantum circuit. Did I screw it? Hopefully I didn't get anything else up. Get state vector. Why not? Results. Oh, we didn't call result. It's early in the morning. Coffee's still setting in. Cool. Okay, so we have our rotation, our measurements. Great. So the first thing I would want to do is let's plot block multi-vector, and then we will do the original state vec. Cool. Run that. All right. So that's how the original state vector appears to us before we've done anything, for any Hadamards or anything. So it's just a quantum circuit. We do a couple rotations on the y. That's what it looks like. Okay. So now let's do orig counts equals q.execute, and we will execute that circuit. We're going to say back end equals the chasm underscore sim. Shots will be 1024. I'm going to make this pep8. And then we will do .result.get underscore counts, and then we will plot histogram orig underscore counts, and then legend equals. Probably don't even need a legend here, honestly, but I'll put it in. So this is our distribution. So it's going to be important because first we're going to, whoops, I'm trying to get an above here. First, what we want to do is uncertain qubits, let's say. So this is for uncertain qubits, just naturally, this is what they look like. Now what we're going to do is we're going to do uncertain qubits Hadamards at front. Okay. So all we're going to do is we're going to take this, copy, paste, and now we're just going to add 2 Hadamard gates to the beginning. So Hadamard on 0, Hadamard on 1. That's our circuit. Cool. We don't actually want to say orig state vector. That should be reserved for the original. And then we're going to do the counts as well. So we've got state vec, draw. I guess we'll do everything in the same order. I don't want to make it confusing as I'm scrolling through here. Orig, state vec, or actually state vec. Did we not run? No, we did run this. I think I just ran it before I made the change. So as you can see, the single Hadamard actually made kind of a significant difference, right? So there's that. And then let's go ahead and plot. So like, okay, that's how it impacted the actual block multivector, but how does it impact the actual distribution? So let's do this. So like, how do these actually collapse? What would it actually end up looking like? So counts, and then I'll just paste counts. So if we look at this, and in fact, let me just to make it easy, I'll get rid of this after we're done. But so this was the original. It looks as though probably 0, 1, and 1, 0 are unchanged. But really what happened is everything just flipped, right? So now 0, 0 is as frequent as 1, 1 was. These are stay the same because they flipped. And then 1, 1 is, flipped basically with 0, 0 from the original. So applying the Hadamard did something kind of funky here, because instead of, they were already uncertain, so then you applied the Hadamard, and then it flips them around, right? And also changed that multivector pretty significantly. But that's a Hadamard in front. Now, what about the, let's say a Hadamard sandwich on uncertain qubits? And all we're going to do is take this, paste, and now we're just going to wrap Hadamards on the other side. So now you can see Hadamard, 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 Hadamard. So it's just squishing in these qubits around Hadamard gates, hence the Hadamard sandwich. So now let's take this, let's look at the state vector that this produces, and let's go back up to the original, just because I think scrolling around is kind of confusing. And in fact, I'm just going to delete this because I don't want to look at it. And come down here. I just don't want that to be confusing. Now when we look at these, isn't that interesting? So this is the Hadamard sandwich. This is your original no Hadamards. Now this is on, again, uncertain qubits. That starts to look like, wow, it's almost the same. It's just kind of flipped, right? But doesn't it look like, if you were to guess where these are going to collapse, would you not guess that, like, if I was to guess, I would have guessed that this whole, like, flipped output would be what happens actually at this point, right? Like, because they look like they're opposite. Right? So I would expect that kind of flip there. But instead, spoiler alert, here's the Hadamard sandwich distribution, right? Counts, regular counts, just the circuit we just ran. That's what that looks like. Now, let's go up to our original distribution. I'm just going to copy it, scroll down here. Hadamard sandwich on top, original on bottom. It turns out they're the same. They give us the exact same output on the distribution. But so what happened though? What happened for us is, even though the output is the same, so the circuit output's the same, what we got was the possibility to, like, at this point, with these qubits here, we could have done something interesting at this stage in the circuit. We could have had another qubit that does something else that works off of this state here before we get to the final Hadamards and then take our measurements. So if we add one more qubit, we can do something based on this superposition state that is basically querying all of the possibilities of input into the circuit without impacting the actual output, which is very interesting. So that's with an uncertain uncertain qubits. The next question is, how does this look in front of certain qubits? So imagine, let's go with, I guess we'd just do the same thing, and then we'll do maybe a not or something. So that was uncertain qubits. So let's just come down here, and let's say certain qubits. And just for the record, all of this that I'm showing is completely applicable to the Deutsch Jozsa algorithm, as well as all of the other fancy ones that everyone's ever heard of. This is the concept that is important. So I'm not just wasting your time, I promise. So now let's look at Hadamard. Let's look at certain qubits. Again, I don't know if that's the right word. That's what I'm thinking of when I look at these. I'm like, okay, this is always going to collapse in such a way. So rotation on Y is uncertain. But we could either do nothing, or just to do something, let's just do a NOT gate. Okay, so we'll just say CX and then CX here. So that's our what we've got now, and then we'll just take this the state vector here. So now what we do is let's apply a Hadamard on Hadamard in front of certain qubits. Whoops. And then I'm going to make some space so we're not constantly dealing on the bottom here. So now what we're going to say is C.H 0, and then we will do at the 1 draw. We don't want to call this original state vec anymore. Oh, I kind of want to do the I'd like to do the original counts as well. Let's go ahead and let's get that done as well. So let me just pop that in here. So just B for bottom will give us that. So there's the I guess we'll do the vector, and then we'll do this. Should give it to us? I want to make sure I haven't made some sort of silly error here. We should just get 1 though. Right. So we always get a 1 1. Okay. So then we throw a Hadamard in front of everything, and then change this to be state vector. So we'll run this circuit. Cool. So now there's Hadamards in front, and now we've got this sort of situation where it's like just fully pointing towards that X. Then what we're going to do is let's look at the counts now. I mean, you should kind of know what to expect. So again, like I've tried to kind of do this every time, but applying a Hadamard to, let's say, a NOT gate, what should be the distribution output here? So let's see. Orig counts, just counts. Whoops. Cool. So it's what you hopefully expected, right? It's just a perfect distribution of all of the possibilities here. So again, don't forget, this is a point where I want to stress that in order to get that distribution, we had to take many shots, right? In order to know that this circuit, like if we couldn't look into this circuit, in order to know what the distribution this circuit had, like in order to know that characteristic, we had to take a lot of shots. So if I just said 1 shot here, we get one type of result. This is not informative to us as to the characteristic of the circuit. Okay, so it just happens to be the case that when we take many shots, because of the superposition state here, we get a distribution. But what we're building up to here is the ability to know a little bit about what the output should be based on this Hadamard sandwich. So, okay, back to what we're doing. So we've got Hadamards in front, right? Now, let's do a Hadamard sandwich. So Hadamard sandwich, certain qubits. So we paste that in, and then Hadamard 0, 1, Hadamard 0, 1, draw the circuit. Looks correct. Nice little sandwich going on there. And then we will do our multi-vector. Okay, now that is the opposite of this. And recall, that is also exactly what happened here. It was the opposite. And if I'm being honest, I still don't totally understand how we're getting a collapse to me, this should have collapsed mostly to 1, 1, but it doesn't. But coming down here, this should collapse, right? Oh, it's flipped. So this should collapse to 0, 0 every time, right? Like if this doesn't, I quit. Because I have to work in I have to work at least with some rules, okay? I understand some of these things are kind of funky, but come on. Without rules, what are we? So, savages. So, oh, we already plotted the multivector. What I want is the counts. So we come down here, and we do the counts. Now this is our Hadamard sandwich on certain qubits. And what we do get in this case is actually flipped values. Okay. Which is still pretty interesting behavior, and it's important to take note that a certain qubit will respond in this way, and an uncertain qubit will respond this way. So what does that tell you? So getting back to our Deutsch Jozsa algorithm, this tells me, ooh, we can do something interesting here. We can take probably any n number of bits, use a Hadamard sandwich to determine is our algorithm, or is our like little box here going to return to us variable output or not. Now, if we just have what we have here without understanding the inputs coming in, we might still see things getting flipped. But this is the basis right away. 0, 0 for a constant, 1, 1 for balance. So keep that in mind. You've just been shown something amazing. So now that we've done that, what I want to do is propose to you the rest of the Deutsch Jozsa algorithm, because I think a lot of this gets lost when people just go straight to the Deutsch Jozsa algorithm. Now, everything I've shown is still applicable, and it's part of the Deutsch Jozsa algorithm, but usually you just get it coded all the way through, and that's not the point. Or people focus on the black box. That's not the point. That's not what's cool. Like, that has nothing to do with it. So, okay, so now let's go ahead and define our black box, or actually, let's say balanced black box. It's going to take in a circuit, and it's going to output a circuit. So we're going to make our little black box function for balanced and constant. So, so let's go. So for constant, what I'm going to do is make this for in the way that everybody else has presented the Deutsch Jozsa algorithm. So the black box is this balanced, either balanced or constant, and the way everyone does it is with a controlled knot. So I'm going to use it with a controlled knot. But understand, there's so many other things that we can do here besides just the one way that the Deutsch Jozsa algorithm is formulated. And again, this is why the Deutsch Jozsa algorithm is the basis for all these other algorithms. It's not like people actually care to determine whether a quantum circuit is balanced or constant. It's that we can determine that all in one pass, because that one pass can consider all of the possibilities. So anyway, we are going to use what everyone uses. This way, if you are confused, I thought about not doing the typical formulation, but I feel like with a topic like this, at least for me, I've just been scouring the web for just all the resources I can find, and then I'm looking to compare things and just see how one person explains something, how another person explains something. Like in the learning process, it's useful if everyone is at least using sort of the same things. So I'm going to use the same things, but just know that the possibilities here really truly are endless. You're not constrained to this formulation. So anyway, we're going to do a controlled knot from the 0th to the at index 2, which you'll see in a moment. We're going to add another qubit here. So we're going to do this entanglement between qubit 0, qubit 1, and they're just going to entangle with this qubit at index 2. Then we're going to say a constant black box. It's going to take a circuit. Oh, and this needs to return a circuit. So we'll just define our circuit, and then when we're ready for this black box, we'll just C equals C, basically, or C equals black box C. Anyway, you'll see. Pun intended. Okay, so the constant black box, the easiest constant black box is to just return C. We don't got to do anything. So, expert tutorials. Okay, so now what we're going to do is we can define our circuit now. So we're going to say C equals quantum circuit. And again, we're going to have 3 qubits, 2 classical bits, because we don't actually care about qubit number, well, qubit at an index 2. It's not relevant to us, because instead what we're actually curious about is what are the outputs to qubit 1 and 2. So anyway, so what we're going to say now is C equals balanced black box C. So now if we did C.draw, quantum. Oh, I keep forgetting this stupid Q. I'm like, I'm pretty sure I spelled that right. Okay, so as you can see, we started it. We can apply this black box however we feel. So now what we're going to do is encase this in the Hadamard sandwich. So we're going to say basically this, copy, paste, and then we're going to apply Hadamard gates to basically everything. So we're going to say C.H 0, 1, 2, and then you can do this, and in fact I've seen people do this. It's kind of funny, but you don't actually need the Hadamard gate here, right? Which will make more sense later on. You can put it there for symmetry if you really want, but it's unnecessary. So now what we have is the following circuit. So things are starting to get kind of jumbled up. So one option you have when this is happening, especially if you're just trying to make things clear, is you can use this barrier. So for example, you could say C.barrier, and it will create this little line for us. So just a quick example here. Run that. And so now you can see it's a little easier to read, right? It looks a little more linear as far as what's happening. Yeah, at this point, you could Hadamard over here. Like, it's totally possible, and it's fine. But it's hard for us to read it if everything's not in line. So as far as I can tell from looking around, the barrier is used to stop the Qiskit optimizer, like in the back end, that optimizes your actual input circuit before it goes to the quantum machine. That will optimize your circuit. So if you're doing something stupid and wasteful, it appears to me that they can fix that with this optimizer. But so you can use the barrier to stop that from happening. So now the optimizer will optimize this section, and this section. Again, this is my understanding. I could be wrong. But in terms of how I see barrier actually being used, it's just purely for aesthetics. It's purely for making these easier to read. Maybe as I get deeper, I'll find a scenario where I really need to stop the optimizer from doing something, but I haven't seen it yet. So anyway, like I say, I'm a noob, so maybe I'm missing it. Okay, so there's our nice, beautiful Hadamard sandwich. And I think what I'd like to show before, so one of the things that gets added again to make this uncertain is you can add, what you'll typically see is a CX for gate 2, so a NOT gate on quantum gate 2. But before we just throw that in there, I want to talk about what that does, right? Because again, it's kind of missed. And in fact, before, exactly why we want to use this gate. So again, here's our little black box. And if you want to be abundantly clear, you can put like 2 barriers or something, but I think this is fine. So what happens when you have a NOT gate and then a Hadamard gate? What goes on there? So really quickly, again, I'm just trying not to gloss over anything at all here, because I think that from what I've seen, at least when I was going through tutorials, I'm like trying to figure out, okay, but why is every single gate, why are they here? What are they doing? And there's really not explanations for this. And it reminds me so much of why I started doing YouTube tutorials in general, like on just in Python, because I was like, no, you have to explain everything. You can't just skip things. So anyway, what happens? Like, let's see what happens when we have a NOT gate followed by a Hadamard gate. Whoops. So let me I just want to steal our state vec code. State vec here. Come down here. Not that. You don't have to follow along on this step if you don't want. You can just look at it. I'm just trying to show you. This is all in the text-based version too, so don't worry about it. So what was the original Hadamard gate, right? It's this positive x value, right? But if we do a NOT and then a Hadamard, it's a negative x value. What if we start with a Hadamard and then we NOT the Hadamard? What happens? Not what we expected, really. So now, what we're going to do is I'm going to ask a question that I'm hopefully going to remember to answer by the end. And that is there another way to achieve going from here to here that does not involve what appears to be the requirement that you first have a NOT, then a Hadamard? Is there another way that we could do this right here? Think about that. Because again, the Deutsch Jozsa algorithm is not specific to doing things in some perfectly exact way. Instead, it's there to show you that this characteristic is there on like all of these quantum algorithms when you use this notion of superposition. So think about it. Feel free to pause it and think about it or whatever, but at the end I'll show you the answer to that question. Will you go away? There you go. I couldn't get it to go away. Like, you press D, by the way, to get things to go away. If you want cells to the bottom, B, atop, A, like above. Okay, so now that you understand what is happening when we add that NOT, let's go. So we've already got it there, actually. So we'll add that NOT gate. I'm trying to think. I think we're actually completed here in terms of everything we need. The only thing that we need, actually, well, our circuit is basically done, but we're not doing anything with the circuit, right? So let's go ahead and we'll take our measurement. Again, this Hadamard you can add there. I have even seen people throw another X here. For the purposes of what we're doing, no. Now, if you were going to maybe work with qubit 2 at index 2, you know, who knows what you might have here. But for the purposes of actually showing the circuit at work, no, it doesn't have to be symmetrical. Even though it is very tempting to make this a nice, perfect Hadamard sandwich. I'm just saying. So now what we're going to say is C.measure. And again, we're going to measure qubit 0, 1, and we're going to map that to the classical bits of 0 and 1. So here's our circuit. And now we can actually measure these. Let's go to counts. Pasta. So what we get as our response here is 1, 1. So it's not. So what this is, basically what this is informing us is it's not really like the output to the circuit. Instead, this 1, 1 corresponds to the nature of the internals of the circuit or something. It's responding to us the nature of like the probabilities in the circuit. So in this case, this is our balanced output. We're getting ones. Now, if you can continue adding as many qubits as you want. So we've got 2 qubits here. You could have had 30 qubits if you had a machine that could do it. It's infinite. You can have as many as you wanted. You could answer this question of like what's the characteristic of this circuit in terms of is there balanced or constant output. So continuing this, what if we went with, rather than the balanced box, what if we did the constant box? So I think we just called it constant black box. Constant. Yes. Okay, so now we do the counts. Run that again. And what we get is 0, 0. And again, it's important for me, I think, to stress this is 1, 1 for every single shot. So we took 100 or 1,024 shots, but we could have gotten this answer with one shot, right? It's 100%, 1, 1, always. So given a perfect quantum machine, we would have always gotten this response. Of course, quantum machines, again, have noise. So we have to, we can't quite get away with that yet. There's no reason to believe that I know of we can't reach perfect quantum machines, right? But again, fundamentally, we can query these quantum circuits one time and understand what is the variability of this output. That's incredible. It's just one shot through, but it's because of this superposition and Hadamard sandwich that this can happen, right? So that's incredible, right? So again, what does this all mean, and like where do we go from here? It's not really answering the question of, well, basically this algorithm does two things. Like the Deutsch Jozsa algorithm is really the first algorithm that provably, like mathematically, can solve this question, even though it's a relatively useless question. It can solve this question faster than a classical computer. A classical computer would require at least 2 passes through the circuit to answer this question. The next thing, and as you increased qubits, it would get even more complicated than that. So it's faster than it's provably faster than a classical computer in terms of like how the cycle through the circuit. But then also, what's more impressive, it's not impressive that it's faster. It's like, why is it faster though? And we're like, oh, because we can actually query while we're in superposition the attributes of this circuit and output that instead. So then what we can do is, clearly there's more information here, right? It's not just a simple 0 and 1. There's so much more to the story, and we can work with that intra-circuit. That's the real amazing part of all of this. It's not, oh, we did it in one shot. It's, why did we do it in one shot? So with that, we're almost done here. The last thing I want to show you is what I asked earlier, which was, can we, I don't know if I saved it up here. I was hoping to just copy paste, but I don't think I did. Can we mimic, let me just take a circuit real quick. Can we mimic, we'll do 1, 1. The Deutsch Jozsa stuff is basically over. Well, I guess it's not, because I'm going to make a point. But anyway, now we're just kind of screwing around. Again, you don't have to follow along. You can just watch. So we have a quantum circuit. We have a CX 0, so a not, a Hadamard on 0. C dot, we don't really have to draw, but I'll just do it. C dot draw. And then we want a state vector. Where is a state vector code? You know what I'd really like? You know what would be awesome? Qiskit devs. Like C dot draw multi-vector. That's what I want in my life. Because like doing this every time you want to make the drawing sucks. Multi-vector state vec. Okay, so that was that way. And then if we were to flip the Hadamard and the not, so what if we did Hadamard then a not? Because don't forget as well, if we just have a Hadamard, what did that look like, right? It's fully in the X. And then if we have CX Hadamard, so this is the order of a not Hadamard that we have in our Deutsch Jozsa algorithm, we can see, oh, okay, it flips it around, right? So again, if we do, and I'm going to stop drawing it because that way we can do all this in one run. I'm just going to say boop, boop. So again, Hadamard all the way, and then if we put the not gate after the Hadamard, what happens? Nothing happens. But what is actually happening when we go from x to this like negative x? What's going on? How else could we get there? Could we get there some other way? So like from here, could we get there? Of course we can get there. Remember, all the gates are superposition, entanglement, and a rotation. So what if we say circuit.rotate on the y, and we're going to rotate by math.pi on qubit 0. Can we get there? It turns out we can. We can get there after the Hadamard. We could also get there before the Hadamard. So we can throw this rotation on the y anywhere the heck we want. The next question is, does this collapse in the same way as we would hope and expect? Now we could do it with just this circuit, but instead what I'm going to do is let's take everything we've been doing up to this point. So we're going to bloop, take this. Now in theory, right, this is what we're trying to wonder, hey, could we change this? So this knot, as you've already seen, if we put it after the Hadamard, it doesn't work, at least in our simple example. Now I can prove to you it also isn't going to work here. So for example, I'm going to comment that out, and then we're going to move it here. So we'll move it after the Hadamard, and then we'll do, let's just take counts here, copy, come down here. I don't think we need to draw it, so again, I'm just going to run everything immediately. So we get a 0, 0 on the balance box, and then you might be thinking, well, maybe the constant is a 1, 1. Constant black box. It's not. We get 0, 0 across the board. So we've lost our the attribute that was so cool. And we can understand, maybe not the quantum mechanics in the background, maybe we don't understand that, but because when we actually graphed the multi-vector, I don't know where my example went, but when we did, you saw it didn't do anything, right? You had a Hadamard, it was full x. You did a knot, it was still full x. So there's no surprise this is not working. But what about, I'm going to comment that out again. We're going to say a rotation now. So we're going to replace the original formulation where there's a knot before the Hadamard with a rotation on the y instead. So we're going to say math.pi, qubit number 2, or index 2 rather. Run it. Okay, constant is a 0, 0. I don't want to rewrite the whole thing. Probably could have done it by now though. Balanced black box is a 1, 1. So now we're back to the behavior, right, that we expected before. But again, rotation on y, we're doing the same thing with the multivectors as before. But as we've also seen, we can get that exact same behavior, right? And as long as we're getting it before we take this measurement, we should be fine, right? So the question is, okay, can we take this rotation on the y, remove it from there, and apply it here? Where the controlled x, or a controlled knot rather, or not a controlled knot, the NOT gate did not work. So we run this on the balance box. We get a 1, 1. Again, good. That's what we hoped. Now, can we do the same thing and get it on the constant black box and get it hopefully a 0, 0? We can. So I'm going to leave it here and just leave you with this, that again, you don't, the math might elude you as to, and it eludes me why the knot didn't flip the Hadamard back the other way, right? But then, like I said, as I'm just kind of playing with this Deutsch Jozsa algorithm, I'm like, that's interesting, you know, because in theory, you just need to make sure everything is the same. You either have a balanced or a constant, you know, thing that happens at this point. So as long as we do our operation before we get to the C knot, in theory, we should be fine. And then as long as nothing else changes here before the measurements, again, you should be fine. Or as long as before the measurements, you either have a constant or a balance. So anyway, I was playing with it and I was like, well, is there another way that we could get this? Like, I was curious, do we actually have to have this NOT gate here? Like, why can't it be here? And then I plotted the multivector and I was like, oh, it just can't be there. And then I was like, but that's weird. Why doesn't it move the multi-vector? And I'm like, well, what if we do a rotation? Like, surely that will move it, right? And it does. And it works. At least on the sim. So anyway, very interesting. So that's it for now. If you know the proper terminology for a Hadamard sandwich, feel free to let me know. If I've said anything else stupid, feel free to let me know. But yeah, that's so cool. So hopefully you guys are as intrigued by all this quantum computer programming as I am. I'm having a really good time playing around with all this stuff. This is just super interesting, and it's really cool to see all. It's like it's just it's just totally different. You have all these possibilities, and like what we're going to be able to do with that is very interesting to me as we move forward. So again, while this might not be as an algorithm all that interesting, it's very simple, so it's easy to understand. But this concept, this is the inspiration behind Bernstein-Vazirani, which is basically a way that you can encode a bit string into your circuit. And then there's the Shor's algorithm, which is the one that can factor large prime numbers. So factor 4 large prime numbers. So anyway, and in effect break encryption. So, okay, I think that's all. So you thought you were rid of me, but actually I wanted to stress one final thing, and that's in relation to why did the not work, and then the rotation on the Y did work. I didn't make that totally clear. Like it might be like, oh, why did that happen? There's a reason it happens. So what I'm going to do is I'm just going to take this here and real quickly answer that question. So what is a rotation, or what's a NOT gate, right? So with our Hadamard, we've lost it. Okay, I'll just do it down here. So our Hadamard goes to here, or even better yet, let's just do nothing, and then we'll add a NOT gate. So this is our start. We initialize to 0. Let's say we apply a NOT gate. Now it points down to 1. The question though is, how do we get to 1? Right? There's two ways we could have applied a rotation to qubit 0 to make our way to 1. One of the ways is to rotate along the, let's say one of the ways was we could have rotated along the y-axis to get to 1. The other way is we could have rotated along the x-axis to get to 1. The dot x should give you an idea of what happened, right? But what if we say c dot y 0? We get the same result. And you might think, oh, I didn't even know those existed, right? And you also have a control z, right? Because here's your z-axis right here. So, and when we do a cz on what otherwise is already pointing, if you're trying to rotate along the axes that you're like perfectly along, nothing happens, right? So that's why if you have a Hadamard first, you're on the x-axis. So when you try to go and do a cx on the x-axis, you just kind of like nothing really happened, right? But that's why nothing happened. A NOT gate is actually you're just rotating along the x. That's it. So a NOT gate is a rotate on the x math.pi. So like for example, and then we'll say 0, and then we'll just comment this out, right? Boom, and then boom, right? There's your NOT gate, okay? So that is, I just want to make a point that's why the NOT gate doesn't work after the Hadamard, right? Because the Hadamard runs us along the x-axis. So there's really, when we rotate, there's nothing to rotate on. But that leaves us the opportunity to rotate along the y-axis to get back to where we wanted. Hopefully that's a little more clear. I just didn't want to leave you guys with this like notion that there's some sort of magical reason the NOT gate just doesn't work after the Hadamard. No, it's just we're rotating along the axes that we're perfectly along. So there's nothing to rotate. So anyway, that's all. And thank you to my most recent awesome human / channel members, Stefan Bowman, Ryan Howlett, Muna Nasir Zonuzi, Dhruv Gupta, Rayboy Gaming, and Kumar's Glue. Thank you all very much for your support, and of course for all of the channel members. If you want to join, you can click that beautiful blue join button next to the subscribe button. I will see you guys in another video.